I gave you my heart.
Hello everyone, welcome to my channel Physics for AP. And previous we were discussing about the ionic bond, and we have discussed about the properties of the ionic bond. Now today we are going to discuss about the covalent bond and how does the covalent bond forms, and what are the theories, different theories which were came forward to explain about the covalent bond. So as we know, the covalent bond, so which was proposed by G.N. Lewis, and it is formed between similar or dissimilar elements, like how the ionic bond is formed only for the dissimilar elements, but here for the covalent bond it can be formed for similar as well as dissimilar elements by the sharing of electrons. So by sharing of electrons, so here we have some of the examples like F2 molecule, the fluorine molecule, oxygen molecule, nitrogen molecule, methane, ammonium, and H2O, water. Now let us go into the theory which was explained by G.N. Lewis, that is the electron theory of valency. So the electron theory of valency says that the sharing of electrons takes place, and how does the sharing of electrons take place is, now let us see for the fluorine. As we have the fluorine atomic number as 9, so when we write the electronic configuration we write it as 1s2, 2s2, 2p5, 2p5. Now this is the electronic configuration of the fluorine. That is, the first orbit we have two electrons, and the second orbit we have total 5 plus 2, 7 electrons we have it. That means we have to represent 7 electrons in the fluorine as the valence electrons, like that is what we call the valence dot structure. Like if we see the fluorine, so fluorine, and let us draw the dot structure, that is 1, 2, 3, 4, 5, 6 and 7. Now the 7 electrons are being placed around it, that is the dot structure of the fluorine is being drawn out of here. And next, when we take for another fluorine, that is as we are discussing for the F2 molecule, as we write another fluorine, and for another fluorine also have another 7, that is 1, 2, 3, 4, 5, 6 and 7. So we have 7 electrons for the fluorine. Now that is, sharing of electrons should be take place so that it consists of 8 electrons in its outermost orbit. So it should be consisting of 8 electrons. Like if you see for the first fluorine, it has 7 electrons and it need only 1 electron for 8, as well as the second fluorine also need 1 electron to get 8 electrons in its outermost orbit. Now the electron which is needed by the second fluorine will be given by the first, and the electron which is needed by the first will be given by the second, like what we call the mutual sharing. So here these two will be get coordinated with this fluorine atom, and the same 2 electrons will be coordinated with the second fluorine atom. So this is how we see that the fluorine gets shared with another fluorine atom. The same as for oxygen, and we can write this as F bond as F bond F. And at the same time, if we write for oxygen, so oxygen we have atomic number as 8. When we write the electronic configuration, 1s2, 2s2, 2p4. So that is the first orbit we have 2, the second orbit we have 4 plus 2, 6 electrons in its outermost orbit. Now when we draw the dot structure for oxygen, so 1, 2, 3, 4, 5, 6. So 6 electrons are placed around the oxygen, and another oxygen atom when we draw it, so we have 1, 2, 3, 4, 5 and 6. Now if you see here, there is a mutual sharing between these 2 electrons, and also there is another mutual sharing between these two electrons. Like how does the fluorine does? Now this occurs as O bond O, that is, as there are two sharings, two pairs of electron sharing over here, that means oxygen consists of double bond, that is O, a double bond O. Now next coming again for the nitrogen, like N2, when we write the electronic configuration for nitrogen, we write it as 1s2, 2s2 and 2p3. So the outermost orbit has 5 electrons in it. Now let us see the dot structure for nitrogen. So as there are 5 electrons, so we have to represent as 5. So 1, 2, 3, 4, 5. So another nitrogen, same as 1, 2, 3, 4, 5. See, as the upper electrons are being paired, so these are called as lone pairs. So one electron will be get sharing with another electron, and another electron, the lone pair electron, will be shared with another one, and this will be shared with this electron. That means here one pair of electron, here one pair of electron, and here one pair of electron. That means we have nitrogen as a triple bond. So this is the, and the nitrogen has only one lone pair. So nitrogen has only one lone pair, one pair of electrons and three lonely electrons. So this is about F2, and this is about O2, and this is about N2. That is the F2 molecule, O2 molecule, and N2 molecules. Now coming for the another one, which is the CH4, the methane. So when we write the dot structure, first we write the atomic number, the carbon 6, and when we write the electronic configuration as 1s2, 2s2, 2p2. So outermost orbit has four electrons in its outermost orbit. So when we draw the dot structure, so carbon, it has 1, 2, 3, 4 electrons which are placed around it, and the hydrogen, which is H, we have only one electron, that is only one pair of electrons. Now this is one hydrogen, this is another hydrogen, and another hydrogen. 4 hydrogens are being placed out on the carbon. Now here we have one bond pair, and here we have one bond pair, and here we have one bond pair, and here we have another bond pair. So this is how does the CH4, the methane, occurs. Now coming for NH3, now when we write the electronic configuration for nitrogen, 1s2, 2s2, 2p3. So 2 electrons, so 3 plus 2, 5 electrons are present over here. And when we draw the dot structure for nitrogen, we have 1, 2, 3, 4 and 5. Now we take the hydrogen, as 3 hydrogens are there. So electronic configuration is 1s1, so 1 electron. So 1 hydrogen here, another hydrogen here, and other hydrogen over here. So here we have one bond pair, here bond pair, and here another bond pair. Now this is the structure for the NH, there is ammonia, so in case of dot structures. And last one we have the water molecule, that is H2O. So here the central atom will be considered as oxygen, and atomic number is 8, 1s2, 2s2, 2p4. So 2, and we have 6 electrons in its outermost orbit. So we draw the oxygen molecule, and we represent them as 1, 2, 3, 4, 5 and 6. So 6 outermost orbit of electrons have been placed. And coming for hydrogen, we have 1s1, only one electron, and one electron will be placed over here, as here it is been paired, which we call it as a lone pair, and here only one electron has been left. Now this is been bond with another hydrogen atom, and another hydrogen atom gets bond with the oxygen. Now wherever you see the central atom, any element, any atom should consist of 8 electrons in its outermost orbit. Like if you see carbon should have 8 electrons in its outermost shell. That we have see here 2, that is 4, here we have 6, and here we have total 8. Now coming to the nitrogen, 1, 2, 3, 4, 5, 6, 7, 8, total 8. And again coming here for the oxygen, 1, 2, 3, 4, 5, 6, 7, 8. And when coming for the hydrogen is which is near to the helium atom. So as hydrogen is near to the helium atom, we consider hydrogen as a duplet configuration. So if we consider hydrogen as a duplet configuration, the remaining elements which we consider them as the octet configuration, like nitrogen, carbon, oxygen, these all comes under the octet configuration. But hydrogen, as it needs 2 electrons to get filled out, so we take it as the duplet configuration over here. So hydrogen has 2, here also we have 2, here also we have 2 hydrogens. So this is about the covalent bond which was proposed by G.N. Lewis, and this is about the electronic theory of valency. So based upon the valency electrons, there is a sharing of electrons, so that which we call it as the covalent bond. As there are some drawbacks based upon this electron theory of valency. So what are the drawbacks? Let's see over here. So the drawbacks are about the electronic theory of valency is it couldn't explain the bond energy and bond length of the compounds. So bond energy and bond length. So we will discuss about this by bond length. So here we have 2 atoms, and we have 2 atoms consisting of 2 nucleus. Now suppose these 2 are being combined together. Like for example, this is oxygen atom and this is another oxygen atom. Now these 2 are combined to form as O2 molecule. Now when these 2 are combined together, they form a bond between them, and this is the bond between them. Now what is called as the bond length is, it is the distance between 2 atoms starting from their nucleus. That is, from the nucleus of one atom to the another nucleus of the another atom, the length is said to be called as the bond length, and the bond length is measured in angstroms. So it is measured in angstroms, that is the units which we measure them, which is angstroms, or what we call it as the nanometers. Also nanometer, that is 10 power 9 minus 9 meters is said to be called as a nanometer, and as well as 10 power minus 8 centimeters is said to be called as 1 angstrom, or what we can write it as 10 power minus 10 meters is said to be called as 1 angstrom. So this comes for the competitive examinations, like how much nanometer is said to be called as nanometer, 1 angstrom how many centimeters, or 1 angstrom how many meters, that they come for the competitive examinations. And coming to the bond length, as we have discussed it is the distance between 2 atoms starting from its nucleus to the another nucleus of another atom. Now what is meant by the bond energy is nothing but the energy which is required to break the bond. So as both are combined together, as the both are having a bond between them, now to break that bond, the energy which is required is said to be called as bond energy. So the electronic theory of valency failed to explain about the bond energy and the bond length of the compounds, as well as it was also failed to explain about the bond angle, how much angle does it forms, that is, it had failed to explain about the bond angle in the structure. And also that's what we are having here, it couldn't explain the structure of bond angle of compounds. So based upon these drawbacks, so we have another theory which is called as the valency shell electron pair repulsion theory, that is we call it as VSEPRT, valency shell electron pair repulsion theory. So this theory was proposed by Chidwick and Powell in 1940, and it was later improved by Gillespie and Nylom in 1957. So from 1957, this valency shell electron pair repulsion theory was little bit came into society about that how the structures are being formed, like the bond angle between them, the bond length, the bond energy, all those have been explained in the valence electron pair repulsion theory. So what he had explained is the first theory, that is the molecules get the specific shape. So as we have discussed it before, the shapes of the molecules, it is due to the lone pair as the charge clouds repel to one another. That we will discuss now. So the molecules get the specific shape due to the presence of the lone pairs, that we need to remember that. So due to the presence of the lone pairs, so they have their specific shapes that we are going to see now, and the lone pairs occupies more space than when compared to the bond pairs. So lone pair and bond pair, as if you see in the previous what we have discussed here, so these are called as bond pairs. So these are called as bond pair, which has the pairs, the electron pair which is participating in the bond formation, which is called as a bond pair. The electron pair which is not participated is said to be called as lone pair. Now this is called as lone pair which is not participated in the bond formation, and this is said to be called as bond pair which is been participated in the formation of bond. Now if we see here the lone pair, so lone pair repulsion will be greater when compared to the lone pair and bond pair, and lone pair bond pair repulsion will be greater when compared to the bond pair. So you will be getting clear understand what is the sequence of this, what is the use of this sequence, you'll be clearly understanding over here. Now let us get an example of the shapes and structures over here. Let us see for beryllium chloride, this is BaCl2. So when we write the electronic configuration for beryllium, so the beryllium atomic number is 4. So when we write the electronic configuration, we write it 1s2 and 2s2. That is first shell, it has 2 electrons, and the third shell also. Second shell, it has 2 electrons. Now we write the beryllium Be as 2 electrons which can be placed on each other, 1 and 2. Now chlorine, when we write for chlorine, so Cl, we have atomic number 7. So when we write the electronic configuration, 1s2, 2s2, 2p6, 3s2, 3p5. That is the first shell, we have 2 electrons, the second shell 8, and third shell 7. That means 7 electrons will be having for the chlorine. So we have drawn the 7 dot structure, that is 1, 2, 3, 4, 5, 6 and 7. And another for chlorine, here 1, 2, 3, 4, 5, 6, 7. Now if you see here, the one pair which is been lonely over here will be get combined or will be shared with the beryllium atom, as well as here also it will share it with the beryllium atom. Now this is the complete structure for the beryllium chloride. So we write this as Be bond Cl bond Cl, which we call it as beryllium chloride. Now here in this valence shell electron pair, it has successfully explained the bond angle, that it has completely 180 degrees, and it explained the shape which is a linear shape. So linear shape, so the complete bond angle is 180 degrees, and the shape which we call it as linear. So this is about the beryllium chloride. So one example, so beryllium, so when we draw the structures, the lonely electrons get paired with the another lonely electrons of the another atom. So now this is the structure for beryllium chloride. So it has 180 degrees of bond angle, and also its shape is said to be called as linear shape. Now let's go for another example, which is BF3, that is boron trifluoride. So here the central atom is boron, atomic number as 5. So when we write the electronic configuration, we write as 1s2, 2s2, 2p1. That means the first shell has 2 electrons and the third shell has 3 electrons. So when we draw the boron dot structure, so this is the boron, and so this is the boron. So we draw the dot structure as 1, 2, 3. So in 3 places, 1 and 2 and 3. So we have drawn the 3 dots electrons, and Coming to the fluorine, atomic number 9, 1s2, 2s2, 2p5. So first shell 2 and second shell 7. So now we represent the fluorine as 3 fluorines are there. 3 fluorines are having 3 lonely electrons. That 3 lonely electrons will be get paired with this. That is 1 fluorine with this 1, 2, 3, 4, 5, 6, 7, and another fluorine with this 1, 2, 3, 4, 5, 6, 7, and another fluorine 1, 2, 3, 4, 5, 6, and 7. Now if you see, here we have a bond pair, and here we have a bond pair, and here we have a bond pair. So this is the structure for boron trifluoride BF3. So when we simplify it, here F, and here F. So this is the structure for the boron trifluoride. Here coming to the angle, here the bond angle, that is bond angle is nothing but the angle between one bond pair to another bond pair. That is the bond angle, which is 120 degrees, and the structure which we call this as trigonal planar. So we call this as trigonal planar. So as the difference between these two is, here we have only 2 bond pairs, here we have only 2 bond pairs, and when another bond pair has been attached to this, that is another bond pair has came. So as the bond pair repulsion, as there is a bond pair repulsion, the angle before it was 180 has been decreased to 120 degrees. Now another example, like if you see for CH4 methane, so carbon 1s2, so carbon atomic number 6, 1s2, 2s2, 2p2, 4 electrons in its outermost orbit. So we represent carbon 1, 2, 3, 4, and hydrogen we have only 1 electron, so 1, here 1 hydrogen, 2, and here 1 hydrogen, 3, and here 1 hydrogen, 4. So here we have 1 bond pair, and here we have 1 bond pair, and this is another bond pair, and this is the another bond pair. So when we simplify it, we get the structure for methane. So this is the complete structure for methane. So here we have 4 bond pairs. So here we have four bond pairs. Previous we were having 2 bond pairs. Before that we have 2. Now we have 3. Now here 4. Now can you tell me the bond angle, whether it increases or decreases? Yes, as the bond pair increases, the angle also gets decreased. So here also the angle gets decreases, so it becomes to 109 degrees 28 minutes. So it decreases the angle like 109 degrees 28 minutes, and the shape which is called as tetrahedron. So this is the shape for the methane molecule, the tetrahedron shape. So boron trifluoride, we have trigonal planar with the angle of 120 degrees, and this is the methane molecule with the shape of tetrahedron and a bond angle of 109 degrees and 28 minutes, and this is the structure for methane. And we have another last two, which is the ammonia, which is NH3. So let us also see the structure and the shape angle. So nitrogen, we have atomic number as 7. So 1s2, 2s2, 2p3. So first shell 2 and second shell we have 5 electrons over here. Now when we draw the nitrogen as 1, 2, 3, 4, 5, and hydrogen, we have 1 hydrogen, that is only 1 electron is present, so 3 hydrogens are being present out here. So as this is a lone pair, we call this as lone pair, so it cannot participate in the bond formation. So the 3 hydrogens will be combined to the 3 lone electrons over here, which is 1, and here another hydrogen 2, another hydrogen over here, 3. Now when you just simplify it, we get the nitrogen structure as, so this is the structure for ammonium NH3. And coming to the bond angle, so the bond angle will be decreased as 107 degrees 48 minutes. So 107 degrees 48 minutes, the bond angle has been decreased. Why? Because we have a lone pair over here. So when we have a lone pair, then due to the lone pair and bond pair repulsion, here we have a repulsion, and here also we have a repulsion. So automatically the size, the angle gets decreased over here. And the shape which we call it as trigonal, we call it as trigonal pyramid. So we call it as the trigonal pyramid or trigonal pyramidal. So this is the structure for ammonium, that is NH3. So the reason why it has been decreased to 107 degrees 48 minutes, that is due to the presence of lone pairs over here. As there is a lone pair over here, the lone pair and bond pair gets repelled out here, and here also the lone pair bond pair gets repelled over here. Due to that, the lone pair and bond pair repulsion, it gets decreases. And one best example, another example of for water molecule, oxygen, atomic number 8, 1s2, 2s2, 2p4. So we have 6 electrons in its outermost orbit. So 1, 2, 3, 4, 5 and 6. So we have 2 lone pairs over here in the oxygen. Here this is one lone pair and this is another lone pair, and these 2 electrons are being ready to get bond with the hydrogen, which is having only 1 electron, and this has been combined with this hydrogen, nitrogen, hydrogen, and this has been combined with hydrogen. When we just simplify this, so this is the structure for water molecule. So this is the complete structure. So here we have a lone pair and here we have a lone pair. Previous, as we have only one lone pair, so this lone pair bond pair gets repelled and this lone pair bond pair gets repelled. Due to that, the angle decreases. Now again here we have 2 lone pairs. So when there are 2 lone pairs, the 2 lone pairs occupies more space at what we have discussed here. The lone pair occupies more space than the bond pairs. So the greater repulsion will be having for lone pair and lone pair. So here the lone pair gets repelled more, and the bond angle also get decreased, and we have here as 104 degrees 38 minutes, or some we call it as 104 degrees 5 minutes. That gets varies over here. So the structure which we call it as the V shape, or we call it as the bent shape. So bent shape. So this is the structure for the water molecule, the raw structure for water molecule. So we have the angle of 104 degrees 38 minutes. Why? Because due to the more repulsion of this lone pair. So as these 2 repulsions are more, the angle get decreased over here. So this is what we have discussed today. So today we have discussed about the covalent bond, which was proposed by G. N. Lewis, and we have seen about the electron theory valency. We have seen the dot structure of different compounds and molecules over here, and we have seen about the drawbacks about the electron theory of valency. Those drawbacks has been explained by valency shell electron pair repulsion theory, and it was explained about the lone pair and bond pairs. So we have seen the structure of BeCl2, which is the linear and having an angle of 180 degrees, and we have seen a boron trifluoride and having an angle of 120 degrees, and the structure is trigonal planar. And for ammonium we have 109 degrees, which is called as tetrahedron, the shape, and from here onwards we have a bond pairs. Now due to the adding of another lone pairs over here, the bond angle gets decreases, and here we have ammonium, which is having a bond angle of 107 degrees 48 minutes, which is the shape called trigonal pyramidal. And coming for the water molecule, so here also we have 2 lone pairs and more repulsion occurs, and having a bond angle of 104 degrees 38 minutes, and the shape which we call as V shape or bent shape. So here also the valence shell electron pair repulsion theory also has the failures. Why? Because still it is based upon the dot structures, and this valence VSEPRT theory didn't explain clearly about the shape, and it also didn't explain about the strength upon the molecules, the strength between this beryllium and chlorine which we have here. And one more thing is, if you see here for beryllium, so beryllium is having total 4 electrons in its sharing, that is 1 2 3 4 electrons which is being sharing here. So beryllium has 4, as well as for boron also has less than 8. So 1 2 3 4 5 6, so boron has 6 electrons while sharing. Remaining all compounds has 8, 1 2 3 4 5 6 7 8. So carbon is sharing 8 electrons over here, and here also nitrogen is sharing 8 electrons. Oxygen is also having sharing the total 8 electrons. But when coming to the beryllium and boron, so the beryllium and boron, so these two are not following the octet rule, but they are said to be, but they are forming a compound, and which we call this as electron deficient molecules. Electron deficient molecules. So keep in your mind, remember that for the competitive examinations, that the beryllium and boron, they don't follow the octet rule. They have, while sharing the electrons, the beryllium has 4 and the boron has 6, and these type of molecules are said to be called as electron deficient molecules. It's clear enough? Now, right now, thank you for your time, and any doubts regarding about the chemical bond and the covalent bond formation, subscribe the channel, give your valuable comment over here, your doubts will be clarified. And thank you for your valuable time for spending with me. Thank you one and all.